Hello, my YouTubers. This is Roy back again. Running a little delayed tonight. We're under weather. Rainy. Cool. Slow down for children. We got Adam in the house. What's up, Adam, man? Dude, I'm running so late today. What do you mean truncated? So just turn on chat replay when I'm watching back, right? Like right now I can't do it. Right? So here we are, rainy night. Rainy night. So let's think about that rain. Got some water going in the works here. I have it on, Adam. So I think it's on now. I think it's on. All right, coming out of the rain. Let's get this party started. Got some cool topics tonight, guys. Got some good experiments, too. So let's just say that we... All right, so I actually walked in, and I must be walking into the twilight zone because everything went blank. So now I'm sitting down in front of the master's chair in front of the wheel. And Adam, if you're out there, yeah, thank you. Did you notice that I fell off? Is my video clear? Okay. All right. So obviously you can see I have a PMH facing towards us, right? Nice. Cool beans. Who else we got out there? We got 3 people watching. So who's the other guys? Shout out and give a shout out. Who's my buds? Alrighty. I see we got a thumbs up for the buds. All right, so you see over here, Dave Wilk. What's up, Dave Wilk? Glad to have you, man. This is Ed Leedskalnin's wheel here, replica. And we have a PMH turned towards us. And I have it hooked up to AC. Well, it's not hooked up right now, but we're going to hook up that PMH into the wall, directly into the wall. And we're going to do an experiment. As soon as we build up a few more people to watch. Variac, he says, Adam. What, I'm going to make that into a Variac? No, we're going to use that to vibrate. We're going to use that as a vibrating source because of the AC. I'll use one. Yeah. It has to be done in a way to where I'm trying to create a vibration. Okay? So the 60 cycles will create a vibration. And then we're going to pull this green. Can you guys see this green? That's green wire. All right. That's, I think it's about 28 gauge. You can see that wire, right? Give me some thumbs up. Can you guys see that green wire good? See that wire? Yup. All right. Cool beans. It's a great experiment. And before we get into that experiment, we're going to start off with light waves. What is a light wave? All right, so let's start off. Adam, I know you're a smart one on this one. So if I was to draw out and I'm creating a sinusoidal, right? So this side would be magnetic, and this would be electric. This side would be electric, this side would be magnetic. This side would be magnetic, this side would be electric. You guys get that? This is a propagated light wave. A transverse. Electric or longitudinal, he says. All right, Adam. So we're talking about light waves right now. We're talking about this being light. And we're going to treat this as a light coaxial circuit. All right, so we're going to think of this light wave, a transverse sinusoidal light wave. There's your magnetic, there's your electric on the downstroke, on the upstroke. Okay? That's what we're going to start off with tonight. And this right here is going to help us realize that leedskalnin, let's put him down here. leedskalnin. All right, he's got a long-ass name. Hopefully I spelled it right. There's leedskalnin, and we're going to talk about some of Tesla. And we're going to combine some of these experiments into what we're trying to accomplish with this wheel. A couple more things I want to add into talking about a light wave as a coaxial cable. Tonight we're going to talk about taking also the light wave, and in these areas right here are areas where we're pulsing. Okay, these are the 0 point. I'm going to call them areas where there's no lateral, no longitudinal pressure. Okay, there's your longitudinal, Adam, because it's this way and this way, that node. And we're going to get into tonight about nodes. We're going to talk about nodes. We're going to talk about spacing in between a length of wire and how we can create nodes. And we're going to also talk about one more thing that I'm going to bring in here. We're going to bring in some harmonics. And then we're going to talk about the harmonics of what octave. A-U-T. Octave. Oh, what is octave? Damn, spell octave. I'm just leaving it like that. So harmonics and octave. Something like that. We'll get past my spelling, guys. On this octave, O-C-T-A-V. Thank you, Adam. So on this transverse wave, we're going to talk about how to run a linear, longitudinal wave through the center of the sinal wave. And what we're going to do here is we're going to call this center here. That's my boy Adam. He's a music nerd. So in this center, unlike this light coaxial circuit, to where how a light wave transverses and how it has its nodes, this here we're going to talk about using a Tesla longitudinal wave with a, we're going to change the upper parts here of this sinusoidal into a dielectric. Okay, we're going to talk about how to send a longitudinal wave and how to control the wave in through the medium versus a hose and it's going out everywhere. This right here is going to resemblance this right here coming from the sun. Is what you have is a longitudinal sinusoidal constant. On here, this section, we're going to take our magnetic pulse, okay? And this is where I think things come in really handy here in talking about the tripods, but our magnetic pulse. And what we're going to do is talk about the vibration that we're going to create in this wave and how to create different nodes. Let's just go ahead and fire this sucker up. And by doing so, I wouldn't advise doing this at home. This is just nothing more than wound coil plugged straight in. But it'll show a great experiment. And I think this is worth the cost. You guys ready? Fire in a hole. Watch the wire. I'm going to put pressure on the wire. Now also look at what I'm doing with the limited amount of pressure. We are creating nodes in the length of wire. I wonder if you guys, can you see that? Let me back that up a little bit. Maybe I need to turn, can you guys see this wire? So right there you can see the harmonics of the wire. It's hard to keep a constant pressure, but it goes to show you pressure creates the nodes. So we'll talk about that once the vibrating is stopped. Let me get a little bit more tension over here, and then I could apply with my thumb here. Yeah, I'm kind of losing it. My wire came undone over here. Listen to the sound changing. Let's look for the first node. Let me see if I can get this to look a little bit better. Yep, that was a little hard. I guess I won't use the PMH next time. I'll make a little vibrator. Cool experiment to see. This is wired. You can use string to see where the nodes, these areas right here in the length of string. I guess that's why they might call that the string theory, but I'm not sure about the string theory. I don't know much about it, but literally, yeah, PMH has got some heat on it. No big deal. But let's go back to this. So here we are, and we can see that when you take a wire and you apply tension on it, okay? So we want tension on that wire. And we have to have a vibrating source. So we want to create a vibrating source, okay? So if the cool thing about this, the vibrating source could be any kind of solenoid coil. And all it's got to do is just have a oscillator to attach to it, and it would vibrate. That vibration right there would cause our wave. Now, I know to go from this electromagnetic wave is basically what I'm talking about with a light coaxial circuit is electromagnetic wave. And there's your lights, pretty much your light wave right there, as we call visible light, is your electromagnetic wave right there. When we're building Tesla coils, we're actually taking a primary and then we're building a secondary that's set to a frequency, okay? And that frequency of that secondary needs to be matched by the driver circuit, okay? And that driver circuit needs to be tuned. Well, that primary from the driver circuit needs to be tuned to when the frequency of that upper secondary. Now, the top of that and the bottom of that, there's, I would call this transmissions. And these are going to be, say, the transmission line. Now, these lines here that we got to bring out of the writing, these lines here are doing what? You guys want to chime in here? There's something that's going on that we created from having a large capacitance. Okay, a large capacitance being dumped into a primary at a certain frequency. So there's got to be some matching of what? Of this transmission line of its antenna. Okay? So Yeah, well, Q, we'll put Q over here. Now, Q will be the efficiency of said transmission. All right. That would be the Q. Now, how efficient? I mean, right now we're looking at what? The transmitter to the receiver in high voltage transmission, right? In high voltage transmission, we're looking at like 100% out, I think, and we're looking at 10% in. There's so much loss right there. There's crazy amount of loss. And this is what we're going to talk about right now. Especially, I think Ed figured out some things in the midst of him learning about all this electromagnetic. But you can mimic nature here in the electromagnetic circuit, we'll call this, which is nothing more than a light wave, and how we can now stop the explosion of it going out everywhere and keeping it directed. And that's by creating a dielectric on the outside to keep it funneled in. And in a sense, Ed's not talking about wireless, but he is talking about keeping the energy inside the pipe, is he not? The energy inside the pipe now is the most efficient, he says, right? I'm not saying this is a pipe, but this is the medium. So this outside dielectric is the medium, okay? Here's the medium. So the outside dielectric becomes the medium of this transmission. So, here we go. Well, here we go. Waveguide. Adam, yeah, it's a waveguide. But it's being a little bit smarter. It's the dielectric is exactly what we're kind of like getting into, because it's the it gives you, where can I get my pencil? It gives you over here a place to, we'll call that the receiver, and it gives it a place over here, we'll call it the transmitting line right here. And it gives us a place to bypass the electromagnetic to the inverse electromagnetic issue with the inverse square law. And this inverse square law that we have to deal with this setup here can be altered. That's Mother Nature, and we can alter the signal that we have going out. And by doing so, we can create these nodes where we want them. We can move the nodes to be stretched out as long as we can, so we can create a continuing chain. Why do you think Ed Leedskalnin's got chains up, guys? There's a lot of backstory to the chains that Ed has up in his picture. This chain reaction here extends the longitudinal wave, because you can have, if you think about this, if you had a bar, okay, the bar was this long, and if you were to look at its first, say, octave, say if it's a third, and then another third, and then another third, and then another third. I don't think the driving force would stay of the part of the vibration you hear in a tuning fork. Let me go get a tuning fork. There's a part of a tuning fork when it's really in resonant, you can hear it go above and beyond its sound. And let me see if I can. Let me get a better smack at that. Now, you know what's the best thing to hit around here? Let's get this keeper bar for the PMH. Let's smack the PMH. Listen to this higher than resonant sound. So that higher octave that I'm talking about is where you can stretch out the bar. So if the bar, like electromagnetic, there's a point where this bar no longer can be split in half, is what I'm getting at. So that means that the dipole, that's, say, the transmitter here and the receiver here, can't make it over here if this was really the receiver. So you would lose your electromagnetic pulse, electromagnetic wave, about half the distance. If this was 100 feet and this was 50 feet and this was 0. Your electromagnetic wave can only go, say, 10 feet. So here's your 10 feet, 20 feet, 30 feet. So it's 30 feet, 40 feet, 50 feet, 60 feet. So you can extend. Forget about the electromagnetic. Think about why the inverse rotation of the electromagnetic, say, distance between here and here, when it does its spiral flip, it has a point to where it has to come back to a resting point. And that resting point that we call nodes is points of acceleration of electricity. If we were transmitting high power, high voltage through this system here. So basically we would create the pressure of the ether itself, of air as we know it, to be the dielectric source of compressing that field, that longitudinal wave. So the other thing that I wanted to talk about in vibrations and say is that there's parts of of harmonics, and when you get to like the first overtone, you would be dealing with, this would be the first overtone right here. So it'd be 2 nodes. And then when you get to the second overtone, you're just stepping up the chain. Third overtone. So it's pretty interesting how vibrations, that's why I try to show in this wire, the vibrations based on tension. So that means tension needs to be paid attention to. You guys get me? So when you're dealing with a longitudinal transversal wave and you're switching the electromagnetic wave into a dielectric coaxial wave, then you're more focused on tension. And that tension has to be created, not at the point. And remember this. The point of origin, we just looked at that. So basically, Here's the point of origin on creating the vibration to this wire. Now this wire started to vibrate. As it vibrated, if I didn't have the perfect amount of tension to that wire, then we wouldn't have seen a vibration, and we wouldn't have seen our first and second octaves in the harmonics of the nodes that were created and me putting a certain amount of tension. So paying attention to that vibration. So we have to go back to the start of edge wheel. Edge wheel's vibration is its pulse rate. So we're looking to go deep into the Schumann resonance in 7.83 hertz. And by doing that, the machine gives us a pulse rate that's matching the sinusoidal electromagnetic, which I don't have it on this page, but I guess I do in a sense, electromagnetic wave. Let's move something over here. I wanted to... How's the visual on here, guys? Can you see it clear? Notice I got this bar all charged up. I got these stuck. And all kinds of stuff stuck to this wheel. Some good chubbies, right? I shit you not. So I'm going to hold this back. I don't know if I can pull this off with one hand. So I'm going to move this over here. And I was just pulling this off, right? And I was putting it back on. I just got done charging it. Now, watch the light on that one as I keep pulling it off. You know why it's blurry? Because these magnets right now are really charged up. So that light's not going to do anything. Okay. But I'm pulling it off. So these magnets are really, really charged up. So what we're dealing with right now is our electromagnetic waves are sitting and they're moving in this fashion right now. You got your inner spin, you got your rotation as it's traveling from north to south, always north to south. Yeah, I don't know about the blurriness, but as soon as I start doing some cool stuff with the magnets, the phone reacts to it. Retract it. All right, let's see if I can get. Oh, that's so hot. I can't mess with that one. So yeah, we're back into learning a little bit about light waves and how we get our electromagnetic energy and how that moves through space. And it's a sinusoidal. It's obviously has a transverse wave traveling through its own nodes coming through space itself. And then Tesla figured out how to send longitudinal waves in direction. I think that's when he started to get into his beam technology, because he realized that he can send, instead of the center of a natural electromagnetic, whatever is coming through the sun in that, I'm not sure, but the outside and the bottom and the other side being electric and magnetic, over here you're switching dielectric and electric in the middle, and you're creating a coaxial natural in the medium event. And that's by using a certain amount of tension to create enough nodes in the length of your transmission. So that means that every time your frequency releases, it needs to pop. It's whatever it's. See, Adam, when you were talking longitudinal, were you talking about like a vertical, like over here, like a vertical, Adam? Because when you're dealing with, say, an antenna, like a sound wave. Okay, well, that's not vertical. That's this right here is a transverse pressure wave. Well, we got to look at it all as pressure waves. That's what we're saying is that, you know, the sun puts out enough pressure to carry this continuum through its own solar system. So the solar system that sun's pressure allows it to have will reach out. That's why we have, I guess that's why solar systems were created per star. So they knew that its own inverse square law of its electromagnetic wave from the sun to its outermost planet or outermost part of its solar system. It probably so much passes the outer planet, I would think, that it's bigger than we think. Well, I think that when you look at the sun's inverse duality here, that you would have each planet would almost be a node. it's I can't say it is, but I'm just saying it's like if each planet became a resting place, which, Jesus, man, I bet it is almost. So the solar system from the sun, the big sun, you got your little guys going out, some big ones, some small ones, some big ones. These are nodes of electromagnetic wave coming out from the sun. Interesting stuff, though, how Ed ties in Mother Nature. You guys agree? I mean, look at this messy paper. But Ed, in his writings of living things and animals, plants, you guys read that? Anybody read that one? Let me see. Where do I have that? I got it somewhere. So, Mr. Ed, a book in every home. If you guys haven't read this one, you got to get it. I got so much written stuff right here. Minerals, Vegetables, and Animal Life. This is where he really ties in the, I can't say like talking to Ed Leedskalnin guy. What's his name? Poole. R.L. Poole. Secret Schematics. I can't say that this does that, but I would say that this here ties in the universe, because he's obviously talking about cosmic force, and you can take whatever you want out of this stuff, but he talks about gravitation must be caused by matter in the middle of the earth and more concentrated than uranium. That when uranium atoms burst, they release the north and south pole individual magnets that held the atoms together. Then the magnets scatter all around. But when the atoms burst in the middle of the earth, yeah, I know. So he's just carrying on about attraction for the other kind doesn't happen until it reaches the surface of the earth. And I think that's important to talk about, because in the Schumann resonance, I believe that that center, let's say if this was the earth, that center. There's a center of gravity, center of this mass. Let's just start with. So the center of this mass, and it's pretty much floating out there. So there's a center. I guess that's why we might have a little different electromagnetic tilt, sort of like a top, versus saying our pendulum would be straight. That's our, you know what? Our tilt to our planet is our pull and our push from the sun right here. That's what that is. There's a difference in, that's our tuning to the sun's energy, is that tilt. Anyway, guys, all right, so I guess I got to go. We got to call it tonight. I hope you guys enjoyed the video. There was so much more I wanted to cover tonight, but the wife demanded I do tile in the house, and guess what? Homie tiled. So I got the wife happy. Happy wife, happy life, they say. You guys take care, and hopefully you have questions. Leave your comments. Thank you.